Okay, here we have web assigned 4-3 RL circuits. At the moment t equals 0, 22 volt variable is connected to a 5 millihertz coil and a 6 ohmic resistor. Okay, so I can start off by actually drawing our setup here. So that's our battery. This will be our resistor, or not resistor, that'll be our inductor. And then that'll be, okay, it's this coil, it'll be our coil, fine. 5 millihertz, then we got 6 ohmic resistor, and a 22 volt battery. Immediately thereafter, how does the potential difference across the resistor compare to the EMF across the coil? Okay, so the minute this battery is plugged in, this this inductor is going to resist current flow across the other half of the circuit, if that makes sense. It's going to resist it, so it's not going to let any current get past it. So basically, there's no current on the resistor, and if there's no current, then there's no potential difference. So across this resistor, there's 0. The coil itself, the coil has created is a magnetic field? It's created a field where it will accept the resistance change of voltage. It'll accept the voltage, but it'll change direct. Does that make sense? I know what I'm trying to say. I just don't want to say it. It'll resist the change by accepting it, but not letting it pass. Does that make sense? There's still voltage going through it. It just doesn't want it to. Okay, so hopefully that makes sense. All the voltage will be within the inductor because the resisting of change won't be in the resistor. And it's the same question about the circuit several seconds after. Okay, so several seconds after, there's now no immediate change, right? So the coil will no longer have an effect, which means that it's almost as if it's a straight piece of wire. So it's basically like there is no inductor anymore. So the resistor will get all the voltage and the coil will have none of it, because now it's just a piece of wire. Is there an instance in which these two voltages are equal in magnitude? Well, let's think about this. In order for the resistor to go to 0 to 22 and the coil to go to 22 to 0, there's like a math formula. It's called like the mean value theorem or something. But there has to be a point at which the one goes up, the other goes down. That means they have to be equal at some point. So this is in fact a yes. If so, is there more than one such instance for all possible times in milliseconds as a comma separate list if there are no such instances? Okay, so we know that there is in fact one. Now, what equation do we use here? So, back to V equals IR, when in doubt, right? V equals R. Now, this is a derived equation. I don't remember the name of it, if there even is a name for it. But there's an equation we used in class before. And you have to remember to use charging or discharging. Here we're using a charging, because we have a 1 in the front. And if we were to have no 1, then it would be discharging. Because at time t equals 0, E would equal 1. Because E to the first power is 1, so it's 0. Did I get everything in there? I did. Okay, yeah, okay. Now, little intuition here would tell us this voltage value we need, this V, so I can pretend that IR is not there for right now, but this voltage value, for them to be equal, both have to be 11 volts. So that's just for that 11 volts where I'm coming from. So we have 11 volts is equal to RE over R. RE over, okay, 22 volts. Because the R's would cancel and the total E is, 22 volts. and then 1 minus E, and then this is where we start plugging stuff in. So our RT, we don't know T, but we do know our resistance, which is 6. Did I put a negative sign up here? I did, okay. Negative 6 ohms. I'm not going to show decimal points here, but you know they still do exist. 0.05 hertz, because milliamps is negative third. Okay, and then just some manipulation at this point. We have 0.5 equals e to negative 12. Oh, not negative 12, negative 1200. Well, I just did, I divide the 22 to the other side, and then I divided my you know, my negative 65 by 0.05. Okay, 12. Okay, and then we got 12,000 C, and then we do a little natural log manipulation here. Ooh. And then we get 0.578 milliseconds. So that one was pretty straightforward. 785. After 3.3 amp current is established in the resistor coil, the battery is suddenly replaced by a short circuit. Answers A and B again with reference to this new circuit. Enter your answers in volts. Immediately thereafter, V equals IR, right? V is equal to R 130 amps times our resistance, which is 6. Gives us 19.8 volts. Now let's review this question again. Is established new resistor and coil. The battery is suddenly replaced by a short circuit. Answers A and B again with reference to new circuits. Okay. Now, after several seconds, there will be no current. Does that make sense? There'll be a resistor. Or I may have said that completely wrong. Hold up. The way inductors work, and then RL circuit several seconds later. We will be at 0. Okay, so parts A, B, C, those are just conceptual, really. I know they ask for answers, but those are just basic conceptual understanding how an inductor works. And that's just classroom understanding. But we get into part D, and that's more of our algebraic understanding, if you will. And then part E is our application of, you know, our conceptual learning. So I don't know, it's not really, you know, this wasn't really rough. There was a few on there that, you know, that could have been a lot worse, and you know, this one's just one of those feel good ones that you do. This one was definitely a sigh of relief to myself that I was able to actually do it. Again, being someone not entirely I don't want to say qualified, but you know, I'll say, as you can probably tell, I struggle with EMF. But this was a nice one to just, you know, get some points for. Common mistakes, just forgetting, you know, how your inductors work for part A and B, and then part C should, for the most part, be a give me a point. But just know which one is 0 at what time. That could be a mistake. You accidentally swap them. You know, it's understandable. Part E, that's the box on the right. That one you could probably slip up on and just, or mix up the order and put 1920 on the right and 0 on the left, and then you could always just mess up your algebra in part D. So this one's just got a lot of small pieces to it. They just gotta, you know, check your work a few times. That's the best advice I can give you, and just take it slow, because a lot of times you'll complicate things that aren't as difficult as they should be.